When we gaze up at the night sky, we are immediately confronted with a vastness that is difficult to comprehend. Our universe is so large, so incredibly vast, that it's almost impossible for the human mind to truly grasp its scale. Before we can even begin to fathom the size of the entire universe, we need to make a crucial distinction: the difference between the universe as a whole and the observable universe. Scientists believe that the universe is much, much larger than what we can currently observe.
To measure the vast distances between stars and galaxies, we need a unit much larger than anything we use here on Earth. That unit is the light year. 1 light year is the distance that light travels in 1 year.
Our solar system, a cosmic family of planets, moons, asteroids, and comets, all bound to the sun's gravitational pull, might seem vast when we consider the distances we're familiar with here on Earth. But in the grand scheme of the universe, our solar system is just a tiny speck of cosmic dust. To truly grasp the vastness of our own cosmic backyard, it can be helpful to shrink things down to a more manageable scale. Imagine, for a moment, that we could shrink the sun down to the size of a beach ball, about 1 meter or 3.3 feet in diameter.
This shrinking exercise highlights a crucial point about the nature of space. It's mostly empty. The distances between planets within our solar system are vast, dwarfing the sizes of the planets themselves. While our shrunken solar system model helps visualize the vast distances involved, it doesn't quite do justice to the incredible range of sizes among the planets themselves. To get a sense of the planetary proportions, let's line them up side by side.
Having explored the vastness of our solar system, it's time to venture even further out, beyond the familiar realm of our sun's influence, into the interstellar gulf that separates us from other stars. Our first stop on this cosmic journey takes us to our galactic neighborhood, a relatively small region of space within the Milky Way galaxy.
The Milky Way, our galactic home, is a truly awe-inspiring sight. From our vantage point on Earth, we see it as a faint band of light arching across the night sky, a celestial river of stars too numerous to count.
While galaxies may seem like vast, unchanging islands in the cosmic void, they are, in reality, dynamic and evolving systems, often engaging in dramatic interactions with their galactic neighbors. One of the most spectacular and violent events in the universe occurs when galaxies collide. For centuries, humans have wondered if we are alone in the universe. Do other planets orbit distant stars? And could any of these worlds harbor life? In recent decades, thanks to advances in astronomical technology, we have discovered that our galaxy is teeming with planets beyond our solar system, known as exoplanets. The first exoplanet orbiting a sun-like star was discovered in 1995, and since then, astronomers have identified thousands of exoplanets, with thousands more candidates awaiting confirmation. These discoveries have revealed an astonishing diversity of worlds, from giant gas planets larger than Jupiter to small, rocky planets like Earth. Some exoplanets orbit their stars in their habitable zone, the region around a star where temperatures are just right for liquid water to exist on the surface, a key ingredient for life as we know it. While we have yet to find definitive evidence of life beyond Earth, the sheer number and diversity of exoplanets suggests that the possibility of extraterrestrial life, perhaps even intelligent life, is no longer a question of if, but when. The search for exoplanets is one of the most exciting and rapidly developing areas of astronomy, offering a glimpse into the potential for life beyond our pale blue dot. As we continue to explore the galaxy, we can only imagine what other wonders await us among the stars.
Measuring distances across the vast expanse of the universe is no simple feat. We can't just pull out a cosmic tape measure and stretch it across billions of light years. Instead, astronomers have developed ingenious techniques forming a cosmic distance ladder to determine the distances to celestial objects. Each rung of this ladder builds upon the previous one, allowing us to measure distances further and further out into the cosmos. The lower rungs of the ladder rely on direct measurements like parallax, where we observe the apparent shift of nearby stars against the background of more distant stars as Earth orbits the Sun. This method is similar to how we perceive depth using our two eyes. Moving up the ladder, we encounter techniques like using standard candles, celestial objects with known luminosities. By comparing the intrinsic brightness of these objects to how bright they appear to us on Earth, we can calculate their distance. One such standard candle is a type of exploding star called a type Ia supernova, which consistently reaches a specific peak brightness, allowing astronomers to use them as cosmic mile markers. As we look out to even greater distances, beyond the reach of standard candles, astronomers rely on another powerful tool, redshift. Redshift is a phenomenon where light waves from distant galaxies are stretched as they travel through space, causing their wavelengths to shift towards the red end of the electromagnetic spectrum, like a siren sounding lower pitched as it moves away. This stretching of light waves is caused by the expansion of the universe itself. As the universe expands, the space between galaxies increases, stretching the light waves traveling through that space. The farther away a galaxy is, the more its light has been stretched, resulting in a greater redshift. By measuring the redshift of a galaxy's light, astronomers can estimate its distance from us. The greater the redshift, the farther away the galaxy and the faster it's moving away from us. This relationship between redshift and distance is a cornerstone of modern cosmology, providing crucial evidence for the Big Bang theory.
Section 3. Echoes of the Big Bang, the cosmic microwave background. Perhaps the most compelling evidence we have for the Big Bang comes from a faint afterglow of radiation that pervades the universe, known as the cosmic microwave background, or CMB. This radiation, discovered in 1964, is a faint echo of the Big Bang itself, a snapshot of the universe as it existed just 380,000 years after the Big Bang. In the incredibly hot and dense early universe, light couldn't travel freely, it was constantly scattered by charged particles. However, as the universe expanded and cooled, a pivotal event occurred. Protons and electrons combined to form neutral hydrogen atoms, allowing light to finally travel unimpeded through space. This first light from the early universe, initially emitted as high-energy gamma rays, has been stretched and cooled over billions of years by the expansion of the universe, eventually reaching us as faint microwave radiation. The CMB provides a glimpse into the infant universe, revealing subtle temperature fluctuations that correspond to regions of slightly different densities. The seeds of the large-scale structures like galaxies and galaxy clusters that we observe today. Section 4. The limits of our vision. What lies beyond? While the observable universe, with its billions of galaxies stretching out for billions of light years, is mind-bogglingly vast, it represents only a tiny fraction of the universe's true extent. The cosmic horizon, the boundary of the observable universe, is not a physical barrier, but rather a limit imposed by the finite speed of light and the age of the universe. Light from regions beyond the cosmic horizon hasn't had enough time to reach us yet, leaving us with tantalizing questions about what lies beyond our current observational limits. Does the universe extend infinitely in all directions, or does it eventually curve back on itself, like the surface of a sphere? Could there be other universes beyond our own, perhaps with different laws of physics or dimensions that we can't even comprehend? These questions remain at the forefront of cosmological research, pushing the boundaries of our understanding of the universe's nature and our place within it. As we develop new technologies and refine our theories, we may one day catch glimpses of what lies beyond the cosmic horizon, unveiling even more profound mysteries and wonders about the vast and enigmatic cosmos we call home.
Section 1. A universe in motion. For centuries, astronomers believed in a static, unchanging universe. The stars and galaxies were thought to be fixed in their positions, locked in an eternal, unchanging cosmic tapestry. However, in the early 20th century, a series of groundbreaking observations shattered this long-held view, revealing a universe far more dynamic and enigmatic than previously imagined. The first cracks in the static universe model appeared in the 1910s when astronomers began measuring the light from distant galaxies. To their astonishment, they discovered that the light from most galaxies was redshifted, indicating that these galaxies were moving away from us. At first, this discovery was met with skepticism. Could it be that our Milky Way galaxy occupied some special central position in the universe, with all other galaxies fleeing from us? This notion seemed rather improbable and egocentric. A more plausible explanation emerged. The universe itself was expanding. It wasn't that galaxies were flying through space away from us, rather the space between galaxies was stretching, carrying the galaxies along with it like raisins embedded in a rising loaf of bread.
In 1929, astronomer Edwin Hubble made a groundbreaking discovery. He found that the farther away a galaxy was, the faster it was receding from us. This is known as Hubble's law, evidence for an expanding universe. Hubble's law can be expressed as V equals h0 times d. The Hubble constant represents the rate of the universe's expansion. Hubble's discovery was a watershed moment in cosmology. It raised profound questions about the universe's origin and fate.
It's important to understand that the expansion of the universe is not like an explosion, where galaxies are hurled outward from a central point. Instead, it's the fabric of space itself that is stretching, carrying galaxies along for the ride. Imagine a balloon with dots drawn on its surface. Each dot represents a galaxy. As you inflate the balloon, the dots move apart from each other, not because they're moving across the surface of the balloon, but because the balloon itself is expanding, increasing the distance between the dots. Similarly, in an expanding universe, galaxies are not flying through space. They're essentially at rest with respect to the space around them. It's the space between the galaxies that's stretching, carrying them apart like the dots on the expanding balloon. This stretching of space has some rather mind-bending consequences. For example, as light travels through expanding space, its wavelength gets stretched, causing it to redshift. The farther the light travels, the more it's redshifted.
The discovery of the expanding universe has profound implications for our understanding of the cosmos. The Big Bang suggests the universe was once smaller and denser. By measuring the expansion rate, astronomers estimate the universe is about 13.8 billion years old. The fate of the universe depends on its expansion rate. Observations suggest the expansion is accelerating due to dark energy. This concept has opened new research avenues in cosmology and astrophysics. When we talk about the universe, we often focus on the observable universe. But what lies beyond this observable horizon? Cosmologists propose three main geometries: flat, open, and closed. Observations suggest our universe is very close to flat. This implies the universe will expand forever, slowing over time. The shape of the universe has profound implications for its fate. While the idea of different universe shapes is already mind-boggling, the concept of a multiverse takes things to an entirely new level. The multiverse hypothesis suggests that our universe might be just one of an infinite number of universes, each with its own distinct physical laws and constants. One popular multiverse theory is the many-worlds interpretation of quantum mechanics, which proposes that every quantum event spawns a new universe. In this view, every possible outcome of every event happens in some branch of the multiverse, creating an unfathomable number of parallel realities. Another compelling idea comes from cosmic inflation, a theory that describes a rapid expansion of space in the early universe. According to this theory, different regions of space could have inflated at different rates, creating bubble universes with varying properties. These bubbles could be vastly different from our own universe, with unique constants, particle types, and even dimensions. String theory, a framework in theoretical physics that attempts to reconcile quantum mechanics and general relativity, also supports the multiverse concept. String theory's extra dimensions and varied compactifications could give rise to multiple distinct universes, each with its own configuration of physical laws. The multiverse hypothesis remains speculative, but offers exciting possibilities for understanding the vastness of reality. If true, it could mean that our universe is just a tiny part of an unimaginably diverse and infinite cosmic ocean.
The quest to understand the total universe is limited by our current technology. Telescopes, no matter how advanced, can only observe so far, constrained by the speed of light and the age of the universe. However, scientists are constantly pushing the boundaries of what's possible. Future space telescopes, like the James Webb Space Telescope, are designed to peer farther into space and back in time than ever before. They aim to capture the light from the first stars and galaxies that formed after the Big Bang, providing clues about the universe's early history and its large-scale structure. Gravitational wave observatories represent another frontier in cosmic exploration. These instruments can detect ripples in space-time caused by cataclysmic events, like black hole mergers, offering a new way to study the universe's most extreme phenomena and test theories of gravity and cosmology. Advances in particle physics, such as those from the Large Hadron Collider, could reveal new fundamental particles and forces, reshaping our understanding of the universe's building blocks. These discoveries might provide insights into dark matter and dark energy, two mysterious components that make up most of the universe's mass and energy, but remain poorly understood. Theoretical advancements combined with technological progress hold the promise of unlocking deep cosmic secrets. As we refine our models and develop new tools, we edge closer to uncovering the nature of the total universe.
Section 4. Philosophical and Scientific Implications. Theories about the universe have profound philosophical implications. The multiverse hypothesis suggests our universe might be one among countless others. This challenges our understanding of uniqueness and significance. It raises questions about the nature of scientific inquiry. Understanding the universe influences our perspective on Earth's place in the cosmos. The quest to understand the universe challenges our deepest assumptions and expands our horizons.
Section 1. A universe of endless wonder. The universe's scale humbles us, revealing layer upon layer of awe-inspiring grandeur. From our solar system to distant galaxies, the cosmic dance of celestial objects is undeniably beautiful. The universe's story is written in starlight and redshift, stretching our imagination. Section 2. Our place in the cosmic perspective. Contemplating the universe's immensity often leads us to reflect on our own place within it. The Earth, once considered the center of the universe, shrinks to a pale blue dot when viewed from the vast cosmic ocean. This shift in perspective from a geocentric to a cosmic viewpoint can be both humbling and liberating. We are but a small part of something much grander, a complex web of energy and matter woven into the fabric of the cosmos. Yet, we are also a product of this universe, forged from the remnants of ancient stars, our very existence a testament to the universe's capacity for complexity and beauty. Understanding our place in the cosmic order instills a sense of responsibility. We are caretakers of this pale blue dot, the only known haven for life in the vast expanse of space. As we venture further into the cosmos, exploring other planets and searching for signs of life beyond Earth, we carry with us the responsibility to protect and preserve the delicate balance of our own planet. The universe does not owe us answers, but it offers endless opportunities for exploration and discovery. By embracing our curiosity, nurturing our sense of wonder, and working together to unravel the universe's mysteries, we honor the legacy of generations of scientists and explorers who came before us. Embracing the unknown. Despite all we've learned, countless mysteries remain. What is the true nature of dark matter and dark energy? Are there other universes beyond our own? What is the ultimate fate of the universe? These questions are now active areas of scientific inquiry. The universe is a vast and wondrous place full of mystery and beauty.